Imagine a star trapped in a magnetic cage, burning at 150 million degrees Celsius, just miles from a major city. This is not a scene from a science fiction novel, but the literal objective of the most complex engineering endeavor in human history. We are attempting to build miniature suns on Earth, harnessing the very mechanism that illuminates the cosmos. The pursuit of this celestial fire represents humanity's ultimate test of ingenuity when the mechanics of nuclear fusion are explained. The process sounds deceptively simple. Two light atomic nuclei collide with such ferocious force that they merge into a single heavier element. Unlike fission, which splits heavy atoms apart and leaves behind hazardous waste, fusion forces isotopes of hydrogen to combine, releasing a staggering amount of energy in the form of high-speed neutrons. It is the fundamental power source of the universe. The successful mastery of this cosmic engine would irrevocably alter the trajectory of our species. We are looking at the holy grail of clean energy, a power source that produces zero greenhouse gas emissions, relies on fuel that can be extracted from seawater, and carries absolutely no risk of a runaway meltdown. A fully realized fusion economy would render energy scarcity obsolete, reshaping geopolitics and halting the march of climate change. Yet, bringing the stars down to Earth requires overcoming an invisible fortress known as the Coulomb barrier. Because atomic nuclei carry positive electrical charges, they naturally repel each other with immense force. To force them to fuse, scientists must heat the hydrogen fuel to temperatures 10 times hotter than the core of our sun. At these extreme temperatures, the gas transitions into a fourth state of matter called plasma. Managing this superheated, electrically charged soup of ions and electrons is where the long-standing scientific nightmare begins. Plasma is notoriously unruly, acting less like a predictable fluid and more like a chaotic, writhing beast. If this 150 million degree substance touches the physical walls of a reactor, it immediately cools down, killing the fusion reaction instantly and potentially damaging the chamber. Therefore, it must be suspended in a vacuum using invisible forces. The most prominent device designed to achieve this magnetic levitation is the Tokamak, a Soviet-era invention shaped like a massive hollow donut. Inside a tokamak, powerful superconducting magnets coil around the vacuum chamber, generating an intense magnetic field that squeezes and drives the plasma in a continuous loop. It is a masterpiece of theoretical physics translated into heavy industry, attempting to dictate the behavior of subatomic particles through brute electromagnetic force. However, the plasma inside that donut is constantly looking for ways to escape its magnetic confinement. Complex microturbulence and violent instabilities can spontaneously erupt within the charged cloud, causing the magnetic fields to snap and reconnect. These disruptions can hurl concentrated beams of heat and particles directly into the reactor walls. Taming this turbulence is akin to trying to squeeze a balloon perfectly evenly with your hands while blindfolded. To bypass the inherent instabilities of the donut design, engineers developed an even more complex architecture known as the stellarator. Instead of relying on a uniform ring, a stellarator uses a series of wildly twisted, asymmetric magnetic coils that look like a crumpled ribbon of steel. This bizarre geometry naturally compensates for the drift of particles, creating a far more stable plasma, though at the cost of requiring microscopic precision in manufacturing. The sheer difficulty of perfecting these magnetic cages gave rise to the enduring cynical joke that fusion is a technology perpetually 30 years away. For decades, researchers found themselves trapped in a cycle of promising theoretical models that crumbled when subjected to the chaotic reality of plasma physics. The scientific community consistently underestimated the sheer tenacity of nature when forced into states it was never meant to occupy on a terrestrial planet. Today, the culmination of those hard-learned lessons is taking shape in southern France with ITER, the International Thermonuclear Experimental Reactor. Backed by a coalition of 35 nations, ITER is a colossal machine weighing 23,000 tons, designed not to generate electricity but to prove that sustained controlled fusion is possible. It is a cathedral of modern science, built to demonstrate that we can extract 10 times more thermal energy than we inject. The ghost of those early containment failures still haunts the blueprints of this massive facility. To hold the plasma steady, the reactor relies on magnets composed of niobium tin and niobium titanium alloys, which must be supercooled by liquid helium to nearly absolute zero. This creates a staggering thermal gradient, Within a distance of just a few meters, the machine must maintain both the coldest temperatures in the universe and the hottest, even if the magnetic cage holds flawlessly. The physical walls of the reactor face an apocalyptic bombardment. The fusion of deuterium and tritium releases highly energetic neutrons that carry no electrical charge, meaning they completely ignore the magnetic fields. These neutrons slam into the reactor's interior lining, slowly degrading the atomic structure of the metal, making it brittle and radioactive over time. Developing materials that can survive this relentless atomic sandblasting is paramount. To solve this degradation, researchers are designing complex breeding blankets to line the reactor walls. These blankets, often containing lithium, are meant to absorb the high-speed neutrons and use their kinetic energy to generate heat. Crucially, as the neutrons strike the lithium, they breed more tritium, a rare isotope of hydrogen required for the fuel cycle. The reactor must literally manufacture its own rare fuel while it operates. The ultimate metric for all of these interconnected systems is something called Q value, the ratio of energy produced to the energy required to maintain the reaction. For decades, every reactor on Earth operated at a severe energy deficit. Achieving scientific break-even, where the plasma generates more energy than the heating mechanisms pump into it, has been the agonizing threshold separating a fascinating laboratory experiment from a viable commercial power plant. A seismic shift in this pursuit occurred recently not with magnets, but with light. Researchers utilizing inertial confinement fusion directed 192 of the world's most powerful lasers at a tiny gold cylinder containing a frozen pellet of hydrogen. The lasers vaporized the cylinder, creating an X-ray bath that imploded the pellet at blistering speeds. For a fraction of a second, the resulting fusion reaction yielded more energy than the lasers delivered. The echo of that laser-driven ignition forever altered the landscape of energy research. While inertial confinement is currently less suited for continuous power generation than magnetic systems, the psychological barrier of energy break-even was finally shattered. This single event triggered an unprecedented influx of private capital, birthing a new ecosystem of agile startups determined to commercialize the technology faster than the massive government-funded behemoths. This influx of private ambition is rapidly transforming a collaborative scientific endeavor into a fierce geopolitical race. Startups are experimenting with high-temperature superconductor spherical tokamaks and entirely novel containment strategies, hoping to shrink the size and cost of future reactors. The nation or corporation that first patents a commercially viable grid-ready fusion design will hold the keys to the next century of global economic and industrial dominance. Imagine a mid-century skyline where the smokestacks of coal plants and the sprawling footprints of solar farms are replaced by compact, silent fusion nodes. These facilities would hum quietly on the outskirts of megacities, drawing minimal water and requiring only a few hundred pounds of fuel per year to power millions of homes. The entire architecture of the global energy grid would shift from a model of extraction to one of creation. Yet this utopian vision obscures a looming resource bottleneck. The heavy hydrogen isotope tritium is notoriously difficult to produce and currently exists in global stockpiles of less than 22.5 kilograms until those internal breeding blankets are perfected. The initial wave of commercial reactors could face a critical fuel shortage. We are racing to build the engines of tomorrow without a guaranteed supply chain for the very fuel they require to ignite. To bridge the gap between our current limitations and commercial viability, physicists are turning to artificial intelligence. Deep learning algorithms are now being fed decades of plasma behavior data, learning to anticipate microturbulence milliseconds before it occurs. These AI systems can dynamically adjust the magnetic fields in real time, catching and suppressing instabilities that human operators could never react to fast enough. The silicon mind is learning to tame the celestial fire. This convergence of artificial intelligence, advanced materials, and quantum-level engineering represents a profound shift in our relationship with the universe. We are no longer merely observing the cosmic phenomena that forge the elements in our bodies. We are attempting to domesticate them, bringing the raw, untamed power of the stars into the realm of human utility. It is an act of immense scientific hubris, matched only by its potential for salvation. Beyond the terrestrial power grid, the mastery of this technology is the absolute prerequisite for humanity's expansion into the deep solar system. Chemical rockets are far too slow and inefficient for sustained interplanetary travel. Fusion drives expelling superheated plasma exhaust could cut the travel time to Mars from months to weeks, opening the outer planets to human exploration and potentially shielding astronauts from the devastating effects of deep space radiation. The transition period, however, will be fraught with economic disruption. As commercial fusion eventually comes online, the valuation of fossil fuel reserves will plummet, destabilizing nations heavily reliant on oil and gas exports. The global economy will undergo a massive structural realignment, forcing societies to navigate the chaotic dismantling of the old energy paradigm while simultaneously building the infrastructure for the new one. As we stand on the precipice of this transition, the very concept of energy scarcity begins to look like a temporary phase in human development. For our entire history, we have fought wars over finite resources, burning the ancient fossilized remains of the past to power our present. The successful deployment of fusion would sever that violent historical chain, offering a future where energy is limited only by our engineering prowess, not by what we can dig from the earth. The scientific challenges of nuclear fusion remain formidable, a labyrinth of plasma turbulence, material degradation, and extreme thermodynamics. Yet the steady drumbeat of recent breakthroughs suggests that the labyrinth has an exit. We are slowly, painstakingly learning to speak the language of the stars, and when we finally coax that celestial fire to burn steadily within its magnetic cage, we will not just illuminate our cities, we will ignite a new epoch for human civilization.